Hello everyone, welcome to this video. In this video we shall be looking at a result which is about the order of an element in the direct product. We have been studying about the direct product of various groups, say G1, G2 up to Gn. So now we are supposing some element from it, say small g1, small g2 up to small gn. This forms an n tuple. Now what would be the order of this element? That is the question which we shall be answering in this video. So the order of some element in the direct product, it is actually direct product which consists of finite number of finite groups. We have already considered here. So the order of such an element would be the least common multiple, the LCM of the orders of the components of the element. So that means in order to evaluate this order, what we do, we evaluate the order of each of these elements individually and then take their LCM. So this is the result here. Now in order to prove the results, let's move forward and see how we may prove this one, right? So for the proof here, we first of all assume that for each of the groups which are present in this direct product, we assume that G1, G2 up to Gn be the group such that each one would have identity as E1, E2 up to En. Now we are forming the direct product out of these n groups, right? These are finite groups. So for each of these groups we have Ei as our identity. Now what we consider that this right hand side over here is nothing but S and this here is T. Why? Because they are the orders. This is the LCM of the orders, right? So this would be some number, and the left hand side is just the order of this element. So this is also some number. So we assume that this T is nothing but the the order of this element in the direct product, and S is the LCM of each of the orders of G1, G2 up to Gn. Now what we need to prove? We need to prove that T is equal to S. So how we will proceed? We will first prove that T is less than S, and then we will prove that S is less than equal to T, so that from these two inequalities here we would have our equality which we wanted to prove. Okay, so let's see that now, because S is what? It is the LCM of each of these orders Gi. So it implies that it is a multiple of each Gi, being the least common multiple. It is obviously the common multiple, being the least, that is no issue. So S is a multiple of each of these degrees, each of these orders Gi. So that means if we raise this element in the direct product to the power S, we would have each of these elements G1, G2 up to Gn raised to power n S, right? And you see, because S is a common multiple of each of these orders, so that means we would have Gi raised to power S is equal to Ei for each I. This would be true. So that is what we have written over here. G1 raised to power S would be E1, G2 raised to power S would be E2, Gn raised to power S would be En. Why? Because S is a common multiple. So that means it would be greater than the degree here. Sorry, the order here. The order here is T. So Gi raised to power T is equal to Ei, such that this T is the least among all such numbers. However, S is a number which is greater than T. How? Because Gi raised to power S is also the identity element. Why? And now why is so? Because it is a common multiple of the order of Gi, correct? So therefore from here we have T less than equal to S. So why is this so? Because T is the order of each of these elements of this element in the direct product, and hence it is of least degree, such that when we raise this to this power we would have this as the identity. Now we are raising it to some other common multiple which is not least, so then also we would have the identity. However, this index here, this power here would not be the least. That is the point. So we have the first equation here. Now on the other hand, if we consider this g1 raised to power t, g2 raised to power t up to gn raised to power t, that would mean that we can take this power outside whole of our element g1, g2 up to gn. And now because t was the order of this element g1, g2 up to gn, so that means when we take this to take this to the power as t, we would have the identity element here. So from here you can see, you can compare that the term here is equal to this term. So that means the first term here is equal to this first term. So g1 raised to power t is equal to e1. The second term here is equal to this second term. So g2 raised to power t is equal to e2. Similarly, the last term gn raised to power t is equal to en. So this we have as the last term. So from all of this, we can clearly see that when we raise g1 to the power t, we would have e1. And when we raise g2 to the power t, we would have e2. However, what is the order of each of the gi? We do not know the order of each of gi. However, we know the LCM here. The LCM of the least common multiple of all the orders, that is s. And we are again having t as some common multiple, and s is the least of all those common multiples. So therefore, s would be less than t. Right, so let's mark this as equation 2. From equation 1 and from equation 2, we can clearly see that s is equal to t, and this is what we wanted to prove here in this for this theorem. So I hope you understood this result well. Well, that is it for this video. Thank you for watching.